So, hi and welcome everybody to the lecture titled Error Correcting Codes. This is the second part following up with the previous lecture related to error correcting codes. In the previous lecture, if you remember with me, we talked about the basic concept of coding. Why do we need to use coding? What's the importance of coding? And the Shannon-related conclusion related to coding, that you can design a coding scheme that can ensure transmitting your data in a reliable manner while not degrading or affecting your data rate. Now we are in this lecture we will be talking about linear block codes. In the previous lecture we taught you how to do the convolutional codes, and in this lecture we will be focusing on block codes, which is another type of coding, and it's commonly used in wireless communication systems. So let's get started. A block code encoder, it transforms each block of k information message symbols to a block of n code symbols. So this means that if you have a message sequence of, let's say, k number of bits, and after you do and perform the encoding, you will have a code word of n number of bits. In the case when you are using BBSK, each symbol carries only one bit, and therefore the symbols represent one bit. So now note that in the case when you have k information bits, there are 2 to power k possible messages, different possible messages. And this is what we usually consider in our systems. We have message sequence of k number of bits, and you need to encode it. So for large values of k and n, a general block encoder needs to store all 2 to power k code words in a dictionary or a so-called lookup table. So if you were to map each information sequence into its corresponding code word, you would need a lookup table. This lookup table looks like this. You have lookup table, and you have here the information sequence k, and you have here the code word, which is code word, and here the information sequence. And for all the different possible information sequence you might get, you will assign different code words for each one of them. So this way we call it lookup table or mapping table. It's like a database. For each incoming information sequence, you get what? You get a code word. But we don't like this process because it involves exhaustive search process, especially in the detection process is very complex and not desirable. To avoid that, we prefer using inherent encoder that works that can be done using a generator matrix or a transformer. So here together, then let's define what's a block code. A block code of length n consisting of 2 to the power k code words is called a linear n, k block code if and only if its 2 to the power k code words from k-dimensional subspace of the vector space of the n tuple over the field GF2. So now during this lecture we will explain this definition and make it very clear for everyone, so that you understand the general structure and the working principle and all the details related to block codes. But we will follow up step by step. So now, a binary block code is linear if and only if the module 2 sum of 2 code words is also a code word. So if I tell you, if someone comes and asks us whether this block code is linear or not, you tell him, look, give me all the code words you have, and suppose I get 2 of them. If I get the summation of these 2 code words, let's say you have one code word like this, 0100101, and another code word 0111100. You sum them up. Now you sum them exclusive or summation, yes, or normal summation, and you take the module. So you take the remainder of this summation, you take the remainder. If the remainder is also belonging to a code word among the existing ones, then you say your block code is linear. And this is very desirable feature that we like to have in our coding schemes. So now it's the well-known closure property of groups. This linear property is it's very well known in the math, and we usually utilize it in coding. So suppose you have the following messages and you are using 7,4 block code. 7 means that the number of bits of the code word. 7 corresponds to number of bits here in your code word, and 4 corresponds to number of bits in your message. So if I ask you what's the code rate for this block code, you tell me the code rate R is equal to K over N. Yes? What's K? K is the number of bits in the message sequence. They are 4. Yes? What's N? N is the number of bits in the code word. They are 7. So you tell me my coding rate is 4 over 7. Is this coding rate reducing the spectral efficiency of your system, or it's not? So question, is this coding rate reducing the spectral efficiency of your system? Means, is it reducing the data rate of your system? You tell me, usually without coding, the 4 bits, I transmit them with 4 symbols. So you have 4 over 4, which is equal to 1. There is no reduction in the coding rate. But here, for each 4 bits or for each 4 symbols, I'm using 7 bits to represent that. So this means that you are utilizing or using the channel 7 times to send 4 bits. So this is not very efficient. This degrades the data rate, reduces the speed of your internet or the throughput at the receiver. But why do we need to use that? Because it increases the reliability of our system and decreases the bit error rate at the receiver. So if I tell you you have an application that requires much lower bit error rate. If I want an application to have much lower bit error rate, what do? You decrease the code rate or increase the code rate. You tell me. If you want to increase the reliability of your system, then this means that you need to decrease the bit error rate. You can decrease the bit error rate by decreasing the code rate. This means that I can, instead of using 4 over 7, I can use 3 or 2 over 7. However, if my system is very sensitive to throughput and I want to increase the throughput as much as I can, then I can increase R value and make it like 6 over 7. So this basically gives you the relationship the relationship of R with K and N, and how it's affecting the bit error rate of your system, bit error rate and data rate or throughput. So basically, when you increase R, when R increases, this means that bit error rate decreases. Yes, when R increases, bit error rate decreases. When R increases, means data rate or throughput increases too. So these are the relationship. How do you control the bit error rate and data rate? How do you control that? You control that by playing with N and K. These are the two important parameters you always need to be careful with, and by using them properly you can always modify your coding rate and accordingly control the bit error rate and control the data rate at your receiver side, because this is why we are using coding, to improve the reliability of our system and make it easier and make it more reliable with minimal reduction in the bit error rate if we can. This is the goal. And we can achieve this by configuring the K and N values in a very efficient, proper manner so that it gives you the required bit error rate and data rate in your system. So now let's move on and see what we got. You have K equal 4, N equal 7, then you have the number of different messages you have, 2 to the power 4, which is equal to 16. However, now you have 16 different messages, but how many different code words you have in your system? You have, how do you calculate that? You have 2 to the power 7 different code words, yes? Which is equal, if you calculate this using your calculator, you will find it equal to 128 possible code words. Each one of them has 7 bits. True? Now you tell me that among all these 128, I need to select only 16 because I have 16 messages, yes? I have 16 messages and therefore I need only 16 code word. But since I have 7 bits, I can get 2 to the power 7, 128. This means that I need to select 16 from 128. Now this will make it very difficult at the receiver side to guess which 16 among those 128 are being selected. Of course, how if you are using systematic encoding, then in this case you will reduce this number of possibilities. Okay, in systematic encoding, because in systematic encoding you have at this part, last 4 bits, you have the message. You have the message here. This becomes the message because it's similar to these. These are similar. The code, this part of the code word is similar to the message, and you are only playing with the remaining side here, and this is the one responsible for determining the code word you have used. Then it will make it much easier for the receiver to decide the possible code words that might have been used. So here the linearity, we care mostly now. We need to obtain the code words from the messages. How do we obtain that? We have 2 methods. Either we use lookup table, mapping table, or we use generator matrix. Now the linearity condition allows us to define a simple encoding architecture for linear block codes. Any code word V in NK linear code C can be written as a linear combination of K linearly independent code words. So what does this mean? This means that if you have a code word V, yes, code word V, and this code word is basically representing a message, and you select this code word from among all the possible code words that you can use for your transmission, then any code word V can be written as a linear combination of K linearly independent code words. This means that you have these linear independent vectors G0, G1, Gk minus 1, and these are multiplied by the message bits, and once you multiply them with each other, you get the code word. Now I can take 0 or 1, and I can be 0, 1 up to K minus 1, and in this case V is the linear combination of all these linearly independent code words G0, G1. Now, how do you let's simplify this for you. Instead of writing it in linear algebraic form, you can write it in matrix form. Let's see. For example, this equation, you can write it like this. V, which is small, let's use another color. V, which is vector, is equal to U, which is also vector, multiplied by G. We call U the message signal, which can be, in the case of of using code word of 4-bit, code word of 7 bits and message length of 4 bits. In this case, your message can be U0, U1, U2, U3. This is your message, which U0, U1, U2, U3 can be either 0 or 1, 0 or 1, 0 or 1. And G, we call this the generator matrix. This is matrix, contains also zeros and ones, and maps the U information bits to V code word bits. So the dimension of this G is 4 by 7, according to the code word we are using, 4 by 7. So for each 4 bits from the message, you get an output code word of 7 bits. So the V here will be something like another vector like from V0, V1, V2 up until V6. So this is the resulting code word after the multiplication process. So alternatively, we can group the linearly independent code words to form G. These, as I did now, the matrix G is the generator matrix, and this matrix is composed of the linearly independent code words G0, and the values of these are zeros or one, zeros or, but this is vector of zeros and one, and then you get this matrix G00, G01, G02 until you finish with Gk minus 1, n minus 1. So what's the dimension of G matrix? The dimension of G matrix is 4 by 7, where 4 is the number of bits in the information message signal, and 7 is the number of bits in the code word. Now, after all, it's much more efficient to have an encoder rather than a lookup table. As I told you before, you can have either lookup table or generator matrix. Why it's more efficient to have generator matrix rather than using a lookup table? Why don't we prefer to use lookup table? Lookup table seems more straightforward and much easier to deal with. Because if you use lookup table, you need to store this lookup table at both the transmitter and receiver, and this takes some space in your memory. Yes, this one aspect. The second aspect, it increases the complexity a little bit, because you will always, especially at the receiver side, when you receive a call, when you receive a message, a signal, you need to search all the possible code words in the lookup table and see which one gives you the minimal error in your detection process. So it kind of increases the complexity of your detection, and it's not very recommended in terms of complexity. That's why we prefer to use encoder rather than using lookup table. Now, having said this, what will you get? If U is the message signal given as a vector from U0 to UK minus 1, and this is to be encoded, the resulting code word can be obtained using V equal U multiplied by J. Multiplied by G, as you can see here. Where is that? Here is the, this is vector, V is vector, contains zeros and 1. U is vector, contains zeros and 1. G is a matrix containing the linearly independent code words. We define them before we start encoding. So now we have these things. So you put your message signal, and this is G. These are the linearly independent vectors. Once you do the multiplication, yes, what will you get? You will get normal multiplication. You go to linear algebra course. Everybody knows how to perform matrix multiplication. You multiply them each message bit with the corresponding column, and you get this result. The matrix G is called the generator matrix for the code word table. Note that any group of k linear independent code words of C can be used to form a generator matrix. Any k linear independent code words, you can use them to actually build the generator matrix. Each different group corresponds to a different mapping from messages to code words. Yes, each different group corresponds to a different mapping from messages to code words. And let's take this example. A generator matrix for the 7-4 block code. The generator matrix is G0, G1, Gk-1. Now, look at this. G0 here, G0 is the is independent code word. The value of this is this vector, Now, let's see this linear independent code word Gk-1 corresponding to this vector, and this is linearly independent code word. Now, let's assume that the coming information message signal is U. This is U is the information sequence, we call it, or the message sequence. And I ask you to encode this information sequence using linear block codes and give me the result, which represents the code word that you are going to send it through the channel to the receiver instead of sending the information signal directly. So what do? You say that I already have the generator matrix, I already built it or given to me, and I have the U. All what you need to do is to multiply them with each other. This U vector with the matrix, and you get this vector, which we call it the code word V. So instead of transmitting this, now look, instead of transmitting the information sequence directly through the channel, you don't do that. You don't transmit over the channel directly. What you do instead, you encode it, you take this information through a block, we call it encoder, and this block performs matrix multiplication with the generator matrix, and you get V. So you transmit V through the channel, not U. V, you transmit through the channel. Now, after you get the result V, you can check if you have made any mistake or not. By what? By just coming here and seeing. If you are using a systematic encoder, then the message signal, the message information should appear in the code word. So you have a message sequence or information sequence of 0, 1, 1, 0. You can get it here, 0, 1, 1, 0. And this is very, very critical and very important, because we need to be aware of and we need to use it. So basically you have the message signal, the message sequence inside your code word, and the other added bits to your code word, we call them the parity check bits. These bits are the ones responsible for detecting whether your message has an error or not. Where are the parity bits? Where are the bits that are added to the message in order to check whether your message has an error or not? It's this 100. Let me highlight it by using a different color. 100 are the parity bits or the checking bits that are used to check whether there is any error in the message or not. So this is how you encode your data. A desirable property for linear block codes is to have a systematic structure. As I told you before, systematic structure means the information sequence bits, the bits. You have them in the code word. Inside the code word, you have them after you perform the encoding process. To have the message symbols appear in the code word, this we call it systematic structure. If your encoder does not show your information bits inside the code word consecutive to each other, this means your encoder is not systematic. And this is not very desirable in practical coding systems. So you will get something like this. The message part will be in certain position of your certain side of your packet, and the redundant checking part, we call it parity part sometimes, in the other side of your packet. Usually it's at the beginning of your packet. So you have K symbols, K bits, and the remaining parts of the packet are for the checking part. Let's go back to the example of 7/4 code linear code block. So when you have systematic encoder, the message is 0000, 0001, 0010. You will have all of them in your code words. Yes, this is the relationship. This, as you can see here. So you have the bits here, the black ones attached to this message, and the next message is here. This message is here, and the blue bits are basically the redundant checking part in your code word. These are responsible for detecting the errors in the information bit sequence. Now, the systematic structure of the code imposes a special structure on the generator matrix. This is the special structure you have. You have a new structure. You call it now the generator matrix. You have an identity matrix to the right side of it and parity matrix to the left side of it. So where is the identity matrix? This is the identity matrix here. This identity matrix is responsible for displaying your information bits in the code word at the end of the code word. This is unity. As you can see, all 0 except the diagonal has unity values. What about the parity? These are the parity bits, we call them, and these are the ones responsible for detecting if there are any errors. So the symbol P means parity, and it can be 0 or 1. G can be rewritten as G. Instead of having only G, you can just put, instead of G, P and I. I for the message, identity matrix, and P is the parity. What's the size of P? Is K plus K, the number of rows is K, and the number of columns is N minus K. Because K of the bits for the message, then the remaining, and N for the code word, then the remaining ones are for the parity. Produces the N minus K parity symbols, and K is the K by K identity matrix. Yes, K by K identity matrix. So in this case, V is equal to U multiplied by G, and this gives the equality that V at position N minus K plus I equal to UI. Yes, this means, this shows that the message is displayed at the code word for these positions. And VG, the parity, is for J equals 0 to N minus K minus 1, which is corresponding to parity bits. This is to the parity part. In this case, V, the value of V at the beginning of the packet, the encoded packet, we call it the code, is equal to U0 P0J until UK minus 1 PK minus 1J. Now you might a little bit feel confused because of the symbols, but now with an example you will understand it much better. Let's go to the example. So here is the example. You have the generator matrix, and in this generator matrix, as you can see with me here, this part represents I. This is identity part, and this part represents P, parity. Yes. In this case, V3 is equal U0. The output here, when you multiply U with G, you will have what? You will have V, the code word vector. Now, in that code word, let's say V, yes, this is V. And this, since this is vector, then you have V0, V1, V2, V3, V4, V5, and finally V6. Now this V3, which is here, yes, V0, V1, V2, V3, it's here. V3 is this. V3 in this case, after you encode your message, will be equal to U0. U0, where is U0? It's this. This is U0. V4 will be equal to U1. U1 is the, why I'm saying this is responsible for taking U1, because U basically is this, U0, U1, U2, U3. Yes, this is U, the message. When you multiply it by this unity matrix, you get only the elements at the diagonal which are corresponding to these values. So V3, V4, V5, V6 will be taking the values of the message. This is what I want to show you. V3 equal U0, V4 equal U1, V4 here equal U1, and V5 equal U2, and V6 equal U3. Now what about the other values, the values at the beginning? The values at the beginning are not as easy as the values at the end. Let's see the difference. V0, now I want to learn what's V0. V0 is U1, U0 plus U2 plus U3. How do you get that? U0 is coming from the multiplication of the information. Let me delete this and make it clear for you. U0, the first element in the code word V is coming from the multiplication of the message yes, with the generator matrix G. So when you multiply U with G, what do you get? Let me write it here for you. You have U is this is G, and you have U. U is U0, U1, U2, and U3. So you multiply this with this matrix, what do you get? You get U0, U1, U0 plus U1 plus U3. So this is equal to V0. Clear? So this vector, now you understand from where you obtained it. V0, why it's equal to U0 plus U2 plus U3. What about V1? V1 is the second element in the code word. The second element in the code word is equal to U0 plus U1 plus U2, which is coming from the multiplication of this with this column. So U0, U1, U2, you get V1. What about U2? U2 in the code word, the third element in the code word, U2, is coming from the multiplication of the information sequence with the third column. So when you multiply them with each other, you get here there is no U0 because it's 0. You get only these three ones, which are corresponding to U1 plus U2 plus U3. Now you know the value of the elements inside the code word, and to summarize it, we notice that to each GKN matrix that consists of k linearly independent rows, we can associate a matrix H of dimension n minus k multiplied by n with n minus k linearly independent rows, such that any vector in the row space of G is orthogonal to the rows of H. Any vector in the row space of G, here this is G, this row is orthogonal to the rows of H in the row space of G. So what does this mean? This means that if we want to put it in a definition, a vector of length n is a code word in the code C generated by G if and only if V multiplied by H transpose is equal to 0. The matrix H is called a parity-check matrix of the code. So H, you can obtain it originally from G matrix. You know the generator matrix? You can obtain H from the generator matrix. How do you do that? You put the identity matrix at the beginning and the parity matrix at the end, and you take the transpose part of it. So for the code word, for the code block that has 7 by 4 bits for the information, 7 for the code word, the matrix becomes like the H becomes like this. Where is the identity matrix here? The identity matrix is this. Can you check with me? This is the identity matrix. and this is the parity transpose. But now the dimension of the parity is n minus k, not k, n minus k, n minus k. That's why, what's n? N is 7 and k 4, n minus k 3. So you have identity matrix of 3 by 3, which is this. So this is for this part. Where is the parity? The parity is this. This is the part of parity, and this corresponds to this. These bits are the parity. And if you multiply H transpose with V and you get 0, then V is a code word. This is how you determine whether what you received is a code word or not. Let's give an example. So here you have the block for the block code 74. You have H given as shown below, and let's determine. Let's highlight the identity part of the matrix from the parity part of the matrix. Where is that? Here. You get this is the identity part, and this is the parity part. Note that as a result of the systematic structure, V is V0, U1. Now in general, V, you write it V0, V1, V2, V3, V4, V5, V6. But here, since you have what? Since you have systematic structure, V3 is equal to U0, then you put U0 directly, immediately, you don't delay it. And V4 is U1, that's why you don't put V4, you put U1. V5 is U2, and V6 is U3. Then the parity check equation, VH transpose, H transpose, everybody remember the transpose. If you have you basically convert the rows into columns and the columns to rows. Then the parity can be written as shown below. So in this case, you have V0 plus U0 plus U2 plus U3 is equal to 0. And this is coming from the first row here. Let me put it in a different color. This first row here is representing this matrix. This V corresponds to V0, and here you have 0, 0, then V1 and V2 are zeros, V1 and V2 are 0, and then you have what? You have here U0, and U1, there is no U1 because it's 0, you have U2 and you have U3. What about this? It's coming from this. Originally, V, it should be like V0, V1, V2, V3, V4. But here, since you already have the H matrix, you can obtain the equation related to that as shown below. Here, you don't have V0 because this is 0. You have V1 and you don't have V2. So you have V1 here, you finish the V's, you go to after that you have U0, U1, U2. U0 plus U1 plus U2 equal 0. And finally, this row is corresponding to this vector. So these are the ones you have. Now, how do you build this using a block diagram? Yes? How do you build this using a block diagram? You need to encode this, and at the end of the day, I need to use a circuit. I need to use a circuit to encode that and to transmit it over the channel and let the receiver get the message and then try to decode it. look, your U0, U1, U2, U3, they go directly to the output. So you basically get them from the output directly from here. This line that's coming this into the output directly. This gives you the part related to the message. U0, U1, U2, U3. This gives you. But what about the other part, which is related to the parity here at the beginning? At the beginning, this part, you need to use these equations for it. V0 plus V0 is equal to you take those to the other side, it becomes U0 plus U2 plus U3, and this is corresponding to V0. So here look with me, you have these values, you take U0 and you feed it to this is like a XOR operation, and then here you have also U0 goes to this summer, and V0 here, you have V1 here, and you have V3. And if you just find V0 from here, what's V0? Can you tell me what's V0? The output here. It's as you can see here, it's coming, there is U0 coming to it, and this line U2, and this line which is U3. So U1, U2, U3. And after that, you just look at this part again and determine. So basically, you need to build these equations all together. All these equations are, when you combine them together and try to represent them using a block diagram, you will be able to draw the circuit that can generate the part related to the message and the part related to the parity. And these are this encoder structure in general, you will use it at the transmitter side to determine the output code word. And by using this for any input message information you have at the input here, you will be able to get the code word here that will go to the channel. And this process should be done in an extremely low complexity manner so that it doesn't increase the burden on the transceiver structure. And once you get the data bits, you immediately transmit them through the channel to the receiver, and then you try to, at the receiver side, you have a circuit which is the inverse of this circuit, and it tries that circuit to map the code word, detect the code word that it receives, and it try to find the close. Once you transmit it through the channel, it goes also, there is a noise will be added to the data bits. Yes, there is noise that will be added, and therefore what will you receive? You will receive vector R, and this R vector is not exactly the same as the code word V that you transmitted through the channel, and the receiver responsibility is to try to determine this R, try to estimate it and determine its values and find to which V it belongs, because you have different V's. You have for example, you have 16 different possible V's, and you received R that's affected by the noise. So can you guess which V R is representing? To do so, you need to formulate an optimization problem, and you say which code word, if I put in the optimizer, will give me the minimal error distance. And from this code word, you will also be able later on to detect whether there are errors or not. And once you detect an error, some code words, they enable you to correct these errors, and some they don't. You just detect that there is an error. And if the code word enables you to correct the error, you just go forward and correct the error and then pass it to the upper layers, like from the physical to the Mac and network, and then presentation session, encoding then to the application layer and get your data at the screen, whether it's text or video or message or whatever. So this basically the encoding systematic structure that usually we need to go. Each and every transmitter needs to go through it so that you encode your message and send it through the channel in a very reliable manner. So we can stop here for now, take a break for 10 minutes, and then resume from this point so that we explain more in details about the specific structure of this encoder and how it exactly works and integrates with the other parameters in the circuit. So thank you very much, and meet you after. So hi and welcome everybody to session number 3 on error control coding. So we will continue from where we left off from the previous session. We talked about linear block codes and how they work at the transmitter, and the generation process, and how you can relate the code word to the message sequence, and the generator matrix, how to build it. Now we need to exactly learn in details how we can build the circuit responsible for generating the code words for different types of messages. So let's give an example, and let's say we have the message sequence given to us is shown as follows, and the sequence can be u0 is equal to 1, let's say, and u1 is equal to 0, u2 is equal to 1, and u3 is equal to 1. Yes. And now we need to encode this. To encode this, and of course we are using 7374 block code. 7 means N, and 4 means K, and for this example the code rate R is equal to 4/7. This is the R value we have. Now we need to encode it so you can call this U vector, the message sequence, and you need to get V vector. V is equal to V here, you can define it also as a vector, which is equal to V0, V0, V1, V2, V3, V4, V5, and V6. Do you have V7? No, because you have only 7 elements. N is equal to 7, and since it starts from 0, then from 0 to 6 you have 7 elements. Okay, now if I tell you this is this code, the block code we are using for error control correction, it's basically systematic. If I say systematic, then you immediately take these 4 bits from the message from the message, the 4 bits from the message, and you put them here at the output. You take them from the message 1 0 1 1 and you put them here for these four values. So now you can tell me, since I said it's systematic, this means that V3 is equal to U0, V3 is equal to U0 and it's equal to 1, and V4 is equal to U1 and it's equal to 0, and V5 is equal to U2 and it's equal to 1, and V6 is equal to U3 and which is equal to 1 2. So then you put in the sequence V, you tell me now the sequence V is given as follows. V, the new V I have V0, V1, V3, I don't know their values, but I know the values of the remaining ones. U3, V3 is 1, here I have 1, V4 is 0, V5 is 1, V6 is 1. So this is the code word at the output. Up until now I have this. But what about V0? What about V3? What about V1? Sorry, V1 and V2. V2. V0, V1 and V2. I need to determine their values. Should I put them 0 or 1? I need to know that. How do you know that? How do you do that? You just go to you go to the circuit that we built to generate the codes. The circuit for V0 you need to look here. For V1 you need to look here. For V2 you need to look here. What's V0? V0 is the XOR operation coming from these three lines. 1, 2, 3. Could you please tell me this line from where is coming? This line is U0. And this line is coming from U3. And this line is coming from U2. So V0 is equal to, you tell me it's equal to U0 XOR U3 XOR U2. Okay. What's U0? U0 I define it to be 1. I give it to you. What's U3? U3 is also 1. What's U2? U2 is also 1. 1 XOR 1, 0. Yes? XOR 1, 1. Then V0 here, the result is 1. Okay? Now let's go to V1. What's V1? V1, let's delete these. V1 is coming from we have these three lines for V1. Let's focus together what V1 is. We have this line is coming from where? From U0. So here we have U0, and this line is coming from U1. You have U1, and this line is coming from where? From U2. So U0, U1, U2, XOR them with each other. So you tell me V1, which is this is equal to U0 XOR U1 XOR U2. And what's the value of U0? U0 is 1. U1 is 0 and U2 is 1. You XOR them with each other, and 1 XOR 0, 1 XOR 1 equal 0. So V1 is equal to 0. Here you put 0. We finished V1. We move to V2. Let's delete these. And move to V2. V2 has also 3 lines coming in, and these 3 lines we need to determine what they are exactly. So let's go to V2 here, different color, use red. So here the first one, this one, let me delete this because it's not showing. We don't need those now. This line, the first line, is coming from U2. U2. Here I have U2. And this line is coming from U3. This line is coming from U3. So here you have U3. And this line is coming from U0. So U0, this line U0, this line U1. So you have V2 here. V2 is equal to U1 XOR U3 XOR U2. So U1 is 0, U3 is 1, U2 is also 1. XOR them, 0 XOR 1, 1. 1 XOR 1 is 0. This is 0. So V2 is equal to 0. Here I have 0. So what's now you were able to find V0, V1, V2, V3, V4, V5, V6. And if I ask you what's the code word that you need to transmit over the channel, you tell me V, which is given as shown below. 1V is 1001011. This is the code word representing the message sequence 1011. To check this, whether it's right or correct, and be able, this circuit is built using the generator matrix G. Yes, not H, G. So when you go back, let's go back to the slides. When you go back, you don't look at this. You don't look at this slide. You look at this slide. This slide. This slide shows you G, and from this matrix you can find V0, V1, V3, V0, V1, V2. And this G is basically implemented with the circuit that you see here, and from which you can be able to find V for any information sequence bit. Okay? This is very critical and very important, and we need to be very careful about it. So now you know how to encode your sequence. If I give you another different sequence, not 1011, if I give you 0010, the answer will be completely different, and you need to recalculate this again. Of course, if I say systematic code and you don't make use of this fact, you will not be able to finish on time. So it might take longer period of time, and you might not be able to even find the answer. So to simplify this for you, I usually tell you that this is systematic encoder, so that you don't spend too much time finding all the values using equations. You just need to find the first 3 values, and then the remaining you put the information exactly as they are in the code word. Okay, Can we move on? We can move on. Let's see. The information symbols are pushed to the channel. In the meantime, they fill in the delay elements. Delay elements here, which are the squares here in the circuit. Now consider for the block code we have NK with generator matrix G and parity check matrix H. And we know the relationship between H and G. Yes, you know the relationship that you basically flip the matrix. You transpose it. Assume that V is equal to V0, from V0 to Vn minus 1 is transmitted over a noisy channel, and R from R0 to Rn minus 1 is received at the decoder. This is now what we have. Let's summarize what we have done so far. You have U as the transmitter. Then using the generator matrix and the encoder circuit, you got V, and then V you transmitted through the channel here through G, the generator matrix, you got V, and through the channel, the noisy channel, you get what? You get R. Now R is equal here at this stage, R is equal to V plus noise, and those both are vectors. And you need at the receiver side, we are at the receiver, we receive this, and we want to determine from R. We don't know V, we don't know noise. You don't know V, nor you know N, but you only know R. From R, you need to guess what was V. Let us define E, which is the error vector, and E is defined as follows. E is equal to R plus V. R plus V is equal to the error, caused by the channel. The noise produced by the channel can flip the bit from 0 to 1 or from 1 to 0. Where EI is equal to 0 for RI equal VI and EI equal 1 for RI not equal to VI for all I values. The vector E is called the error vectors. Now why did I define E in this manner? E is equal to R plus V. Simply because V is the original code word and you transmit it and you receive it at the receiver as R. R is basically summed to the noise. The noise summed to the code word. For example, the noise can change some bits from 0 to 1 or from 1 to 0. Any change in R it's supposed to be V. If it changes to some other values, then you will have ones in the vector E. Ones means there is an error. Let's say V was something like this, 1, 1, 0. And due to noise, you didn't receive it like this, you receive it like this, 1, 1, 1. Where is the error? The error in the third bit, 1. Now, when you XOR them with each other, yes, this is V, this is R. 1 XOR 1, 0. 1 XOR 1, 0. 0 XOR 1, 1. Here you know that here there is an error caused by the channel. If you know that this is an error, yes, this is an error caused by the channel, and you only have 0 or 1 values, then you just flip this back to 0, you get the correct code. If you are using only 0 or 1. This is how you detect and correct. This is just one simple approach, but you have many different approaches. Some of them, they are extremely very complex, that we will explain them in the coming lectures one by one. But for now, you understand how to relate the code word to the received vector and define error vector that can tell you whether there is any error or not, and how to detect it and how to correct it. You can correct it using this simple method only if you are using what? If you are using binary digits, 0 or 1. But if you are not using binary digits, you cannot correct it using this simple method. So we can also write R, the received vector R is equal to V, which is the code word, plus the error E. Now, the decoder at the receiver side must first determine whether any error has occurred during transmission. This process is known as error detection. Please remember this. Error detection process is done at the receiver side during the decoding process to determine whether there are any errors or not. It first to do so. This is the other approach, the systematic approach that utilizes the generator matrix and H matrix at the receiver. What do? It first computes S. S is equal to R multiplied by H transpose. How do you obtain H? H you obtain it from G. And R, you received it at the receiver. From this, you can calculate a vector called S. This vector, it has a special name. We name it syndrome. Syndrome is the vector resulting from the multiplication of the received vector with the matrix H transpose. If S is equal to 0, if and only if R is a code word. If R is a code word, it belongs to one of the code words, then S is 0. You always have S is 0. If the syndrome is not equal to 0, an error is detected. Okay? So this we call it absolute error because you are detecting a code outside of the range of codes you used at the transmitter, and this you detect a code among all the used code at the transmitter, but you don't know which one is really the correct one. That's why we move on to the other steps that can help us determine this. First steps towards error correction. So first, initially you detected that there is an error or not. If the syndrome is equal to 0, R is a code word. If the syndrome is not equal to 0, an error is detected. First steps towards error correction. This is where you start correcting after you detect that there is an error. This is the first connection between the transmitted code word and the received vector. The syndrome is the connection between them. Now, keep in mind that neither V nor E, which means the code word and the error sequence, are not they are not known at the decoder. Only R, which is the summation of both V and E. And this is why we need encoding, and it's a little bit difficult than modulation and the other processes. Because you have the summation of two vectors, and from this summation you need to determine what was the vector, V, the code word. Does this mean we can detect all errors? If E is a non-zero code word, R is a code word and S is equal 0. What does this mean? If E is a non-zero code word, if it is non-zero, this means that it has one element in it, 1, which means that there is an error in one of the bits. But R is a code word and S is equal 0, which means that the code word belongs to the list of code words that we have used at the transmitter. And this means that there are 2 to the power k minus 1 non-zero code words there are 2 to power k minus 1 undetectable error vectors. Okay? From where is that coming? Because we said we have 2 to power k messages, but the number of different error codes is like 2 to power n. And you are not using all of them, you are using only subset of them, which is the number corresponding to the number of different messages you have. So among all these, you have 2 to power k minus 1 non-zero code words, and therefore 2 to power k minus 1 undetectable error vectors. Let's give an example, practical, realistic example. For the linear block code 7.4, you have the received code, the received message or the received signal R0, R1 till R6, and you have H which you obtained it from G. Then by multiplying R, the received vector, with H, you get S. S is the syndrome, and the vector length is equal to, the syndrome length is equal to n minus k. If n is 7 and k is 4, we have syndrome, length of the syndrome will be 3, as you can see here. So the syndrome S0, S1, S2 is equal to the multiplication of this vector with this column, and this vector with this column, this vector with this column. The first vector, the received vector with the first column gives you S0, which is equal to R0, R3, R5, R6. And S1, which is the multiplication of R vector with the second column, is equal to R1 plus R3 plus R4 plus R5. This is R5. And S2, which is this element, S2 is coming from the multiplication of this vector with the third column, which is equal to R. You don't have R0, you don't have R1, you have R2. R2 is here plus R4 because R3 is 0 plus R5 plus R6. So you have the syndrome here. You were able to obtain the syndrome. You can draw the correcting shift register based syndrome circuit similar to this circuit now. From the three equations, see here we have V0, V1, V3. You can also draw a circuit for the syndrome similar to this, but instead of V's you put S. So here are the equation S, S0, S1, S2. You obtain them from the received vector R0, R3, you receive the bits in the vector, you put them in the circuit inputs, and from there you calculate S0, S1, S2. And this is the answer for this question. Draw the corresponding shift register based syndrome circuit. Now mathematically, how do you do that mathematically? Let's try to understand the significance of the syndrome S by math. S is equal to R multiplied by H transpose, as I showed you here. And the length of S is n minus k. Now, what's R? R, everybody knows that R is coming from the summation of V with E. V is the code word and E is the error caused by the channel on V. And you multiply it by H transpose, which is coming from G. But you just put the diagonal matrix element, unity matrix at the beginning and parity at the end, and you change the dimension. Then now you can distribute this. V. You can multiply V with H transpose and then E with H transpose. You get VH transpose, EH transpose. And since V with H transpose is always 0 because it's a code word, what will you get at the end? You will get E multiplied by H transpose. So the syndrome, when you multiply when you multiply the received signal with h as if you are getting this. E multiplied by h. These are equal. So S is equal to this, E multiplied by H transpose, and rewriting the syndrome equations for our example according to the new representation gives the following. For the 7-4 linear block code, S is equal to R multiplied by H transpose, which is equal to E multiplied by H transpose. This gives you these values that we already obtained previously here. So here S0 is equal to E0 instead of R. These equations are exactly the same as the previous equations I showed you here, but instead of R you put E. And this is coming from H. You put S0 equal E0 plus E3 plus E5, E6 and so on, and you continue in this pattern. You find S1 and S2, and then even though the decoder does not have access to E directly, because it doesn't know E, it doesn't know E nor does know V. Both of them are unknown to the receiver. However, it can operate on it indirectly through the syndrome. From the syndrome, it can operate on it. So the syndrome S is available at the decoder. Yes, we can obtain it by multiplying the received vector with H transpose, which becomes equal to R multiplied by H transpose. Can we solve this equation set that we found here? Equation set, this one. We have n unknowns, n minus k equations. N minus k, which means for the case of 7-4, we have three equations. We have three equations, but we have 7 unknowns. And to the solution for this problem, this we call it, we have infinity number of solutions. So we can reduce them to 2 to the power k solutions, because this is underdetermined problem. The number of equations are less than the unknown, and you don't have one. So how can you solve these? You have 2 to the power k different number of solutions. Now, depending on the channel, not all we can exclude some of the error vectors. Not all error vectors in this set are equally likely. The error correction step therefore must choose the most likely one. The most likely one, you choose them and include them in your solution. For a binary symmetric channel, for example, what do I mean by binary symmetric channel? Let me explain the binary symmetric channel this for you. In binary symmetric channel, you have, change the color, you can transmit 0 or 1. Now, if you transmit 1 and receive it wrongly 0, there is a probability for receiving it 0. We call it probability 0, 1. And there is a probability of receiving it 1 correctly. And the 0, if you receive it 0, we call that the reception is correct with a probability, with certain probability that we will write its value later on. And if you receive the 0 as 1, we call that you have made an error. And this error, we call it B10. So now, what's the probability of receiving your bit successfully? It's 1 minus B01. And the probability of receiving the 0 successfully is 1 minus B10, this one. So this channel, this type of channel, we call it binary symmetric channel. Binary symmetric, because for 0 and 1 you have 2 different bits, and you have equal probability of receiving it correctly or wrongly. And if the probability of receiving it wrongly decreases, the probability of receiving it correctly increases automatically. So the maximum likely detection, let's explain the maximum likely detection. The maximum likely is a detection process that finds the code, the closest code that reduces the error. Let me explain it to you. You have R, yes, you received R. R is equal to V plus E, yes? V plus error. So this, the detection, the maximum likelihood, it's something like this. You start guessing, you don't know V, you want to detect V, and you don't know E. So what do? You start guessing what would be the value of V that makes it very close to R. So you kind of define a new problem, R minus V plus E. This is the equation you have, and you try to minimize this value for all values of V. For all V, you try to search the value of V. You already have the possible code words that you think that the transmitter might have transmit. You have all the values of these that the transmitter can choose and transmit to represent the message. So what you do is you search for the value of V that can minimize this result. You have R, you have V, E. So you don't know E, you know R, you received it, and V, you can obtain it from a mapping table or a lookup table because you already know these, all the values that can be used, but you don't know which one of these values. So you define a for loop and you go over all of them one by one. And the one that gives you minimum result here, that reduces this value to minimum value, you detect it as this is the code word that the transmitter used to represent the message. And from here you detect that this was the code word. This is the simple this process of detection, we call it maximum likelihood. As you can see, it's complex process a little bit. Why? Because you need to search for all the codes one by one. Suppose you have 100 codes, you need to use all of them in these equations, calculate the results, and store the data in one element. And again, the second, the third, the fourth, until you finish all of them. And then you compare these all values and find the lowest value. And the code corresponding to the index of this lowest value is basically the code that the transmitter used. So it's very heavy and extremely expensive process in terms of complexity, and it can cause delay and consume lots of power. So it means that chooses V hat is the estimate after the ML detector. Chooses V hat as the code word V as the actual code that the transmitter used. That minimizes the distance D RV. Minimizing the distance RV is this equation. This word means this equation. This is equivalent to detecting an error vector E with minimum Hamming weight. Yes? Hamming weight is like the distance. Here it finds the distance, and because when you find out that the values of R and V, they are ones and zeros, so this becomes like distance. For example, if I tell you you have this vector, what's the distance between them? Here you have 0, 0, 0, you have one square. Yes? How do you find the distance? Distance between these two vectors, it's the square root of the first element minus the second element, first element from the first code word minus the second element in the second code word. So 1 minus 1 square. 0 plus 0 minus 0 square, 0 plus 1 minus 1 square, 0 plus 1 minus 0 square, 1. Square root of 1 is equal 1. So the distance between them is 1. Now, if there is another error, let's say there is another error. Instead of 0 here, you have 1. You will get square root of 1 plus 1, which is square root of 2. The distance now is larger. So which code is closer? The one that has value 1 or square root of 2? 1, of course. That's why you select 1 to be the code representing the closest value. So let v equal 1001011 be the transmitted code word, and R is the received code word is 1. See, I transmitted v 1001011, but R, the received R, if I tell you where is the error, obviously you can detect clearly where is the error. Here is the error in this bit. Here there is an error in the channel. I need to correct that. The R is the received vector, but the receiver, since the receiver, the practical receiver, your smartphone, your smart computer, your whatever device you are using for reception, it doesn't know V. I know V because this is a question, because I designed the questions and I sent V. The receiver doesn't know V, so you cannot easily say that the error is here. The receiver only knows R, but he doesn't know V. That's why you cannot say simply the error is here. And therefore, we need to go through this complex process at the receiver to determine where is the error and how to correct it. Because I don't know V, I only have R. Now, at the receiver just right away tries to find the syndrome S, which is a vector of length k minus n, which is a vector of length n minus k, and it's equal to R multiplied by H transpose, and you already have R from the questions. You multiply it by H transpose. H, you know it. H, you get it from the generator, and you get that the syndrome is S111. Now, this syndrome, you can write these equations. S1 is equal to these values. S1 is coming from, S1 is equal 1, and it's equal to this. E0, E3, E5, E6. And S1 is equal to 1, and this is 1, and equal to E1, E3, E4, E5. And you do the same for S2. We can immediately see that the error vector is 0, 0, 0. After you do the calculation and calculate the values, you find that E is this. How is that? How did you find it? How do you make sure that this is correct? You come and add R to V, to E. If it gives you the code, one of the codes, then this is correct. Once you add this together, you will get this V, and this means that this is the error. Now let's see what the decoder knows here. The following 2 to power k equal 2 to power 4 equal 16 error vectors satisfy this equation set. These are the equation sets that you obtain them from the previous values here. See how complex the process is, and it finds that E is equal to this value is the one with the smallest number of ones, and therefore the most likely one over a binary symmetric channel. Taking E as the estimated error vector, the decoder decides on V equal R plus E, and this is to find V. After you find the error E, you just add E to R and you find V. and you found out that V is this, which is this value that you transmitted here, V. But see how difficult and complex and time consuming the process of detecting the bits at the receiver side. It's not as straightforward as you might think. Like for a human being, when you give him this, you transmitted V and you received R, tell me where is the error by your eye. You can immediately tell that the error is in the sixth bit, which is instead of receiving it 1, I received it 0. But since the receiver does not know V nor E, you just know R. So you need to perform literally several complex processes in order to detect the error. And from there, you add the error sequence to the received vector R to get the estimated vector V. So this is one of the approaches that you can use in order to detect the the code word that you have received from the channel. Now you detected the code word. What will you do next? After detecting the code word, you need to map this code word to the message signal. How do you map this? Using the generator matrix, because V is equal to U multiplied by G. So if you want to know U, you can say that it's equal now to G transpose, G inverse multiplied by V. Or you can use a mapping table. Which way you prefer depends on the capabilities of your system. If you want to avoid using lookup table, you can use the inverse. But if you find the inverse to be complex to be found, you can prefer to use the lookup table method. So with this, we can stop here for this lesson, and we can continue next time with the other detection processes that can be used at the receiver side. So thank you very much for your attention, and see you in the next lesson.